Here we are going to, hi everyone, here we are going to see about the unit 2 infinite impulse response. So in this topic, we are going to see about the characteristics of practical frequency selective filters. Then what are the characteristics commonly used for analog filters, Butterworth filters, Chebyshev filters. Likewise, we are going to see about the characteristics. Then we have to design the IAR filters from the analog filters. For that, we have used the low pass filter, high pass filter, band pass filter and band restrict filters. So next we will see about the approximation of derivatives, then impulse invariance methods, bilinear transformation, frequency transformation with the direct form 1, direct form 2, cascade, parallel realizations. So these all things we are going to see in this unit. Let me see one by one. First thing will be the structures for IAR systems. So the IAR systems are represented in 4 different ways. The first thing will be the direct form structure form 1 and form 2. Second thing will be the cascade form structure. Third will for parallel form structure, and fourth is the lattice and lattice ladder structure. Okay. So first one is direct form 1. So for that we are going to see one of the problem. That is, obtain the direct form 1, direct form 2, cascade and parallel form realization of the system. That is, y of n is given, that is minus 0.1 y of n minus 1 plus 0.2 y of n minus 2 plus 3 x of n plus 3.6 x of n minus 1 plus 0.6 x of n minus 2. So this is we are going to see about the all these realization of systems. So solution is, that is, first we are going to see about the direct form 1. So the question we have to differentiate it, that is 3x of all the x of n should be in one form and another y of n should be in the another forms. So split up the x of n and y of n values. So that is 3x of n plus 3.6 x of n minus 1 plus 0.6 x of n minus 2 equal to w of n. Next is y of n is equal to 0.1 y of n minus 1 plus 0.2 y of n minus 2 plus w of n. Okay. So for that we have to draw the realization formula. So that is the x of n should be denoted here and y of n should be denoted here. So here we are going to see, that is z inverse. So here take this x of n equals. So this is 3. Next is the n minus 1 means 1 z inverse is put. So here 3.6. Next z n minus 2 means another z inverse. So 1 is and 2. So that is n minus 2. So here we are going to use the 0.6. Likewise for y of n. So that is z inverse. N minus 1 means that is 0.1 z inverse. Next n minus 2, that is 0.2 is in z inverse. So w of n. Okay. So this is the direct form 1. Likewise we have to draw for direct form 2 also. So that is h of z is y of z by x of z. So y of z is this one. So 3 plus 3.6 z inverse plus 0.6 z power minus 2 divided by 1 plus 0.1 z inverse minus 0.2 z power minus 2. So for this we have to draw the realization form. So x of n and y of n. So that is x of n and y of n. So we have to form the form. So x of z this side 1. Next is 0.1 z inverse. After that here minus 0.2 z inverse. So that is 0.2 z inverse. Next here 3. Then 3.6 z inverse to the y of n and 0.6 z inverse to y of n. So next we have to form the cascade form. That is y of z by x of z. So that is equal to 3 plus 3.6 z inverse plus 0.6 z power minus 2 divided by 1 plus 0.1 z inverse minus 0.2 z inverse. So first we have to take the common value, that is 3 plus 0.6 z inverse into 1 plus z inverse divided by 1 plus 0.5 Z inverse into 1 minus 0.4 Z inverse. So that is H1 of Z is 3 plus 0.6 Z inverse divided by 1 plus 0.5 Z inverse, and H2 of Z is 1 plus Z inverse divided by 1 minus 0.4 Z inverse. So now we have to realize that is H1 of Z and H2 of Z, and cascaded both to get realization of H1 of Z and H2 of Z. So that is x of n is shown here. So first we have to split up the values. So that is x of Z, H1 of Z should be in the one side and the H2 of Z should be in another side. Both are combined together to forms the output value. Next is the parallel form. So parallel form means that is H of Z is equal to 3 plus 3.6 Z inverse plus 0.6 Z power minus 2 divided by 1 plus 0.1 Z inverse minus 0.2 Z power minus 2. So commonly we have taken that the value will be minus 3. 7 minus 3 plus 7 by 1 minus 0.4 Z inverse minus 1 by 1 plus 0.5 Z inverse. That is equal to C plus H1 of Z into H2 of Z. So we will draw the diagram in the parallel form, and then the output will be get into the y of n. Next we see about the analog filter design. Okay, so there are two types of analog filters. One is Butterworth filter and another one is Chebyshev filter. So the analog low pass Butterworth filter will be mentioned by n value, and for that each n values we will having the denominator of h of s. So they are mentioned here. For 1 we have to use the denominator of h of s as s plus 1. For 2 it is s squared plus root 2 s plus 1. For 3 s plus 1 into s squared plus s plus 1. For 4 s squared plus 0.76537 s plus 1 into s squared plus 1.8477 s plus 1. For 5 s plus 1 into s squared plus 0.61803 s plus 1 into s squared plus 1.61803 s plus 1. For 6 s squared plus 1.93185 s plus 1. Next is s squared plus root 2 s plus 1, s squared plus 0.5176 s plus 1. Okay. For 7 it is the s squared plus s plus 1 into s squared plus 1.80194 s plus 1, s squared plus 1.24 s 7 s plus 1, s squared plus 0.445 s plus 1. Okay. So let me see one problem. Design an analog Butterworth filter that has a minus 2 decibel passband attenuation at the frequency of 20 radians per second, and at least minus 10 decibel stop band attenuation at 30 radian per second. So first we have to write the given data. That is passband attenuation alpha P is 2 decibel and stop band attenuation alpha is 10 decibel. Passband frequency alpha ohm P is 20 radian per second. Stop band frequency ohm S is 30 radian per second. So the order of the filter will be n is greater than or equal to modulus of log base 10 root of 10 to the power of 0.1 alpha is minus 1 divided by 10 to the power of 0.1 alpha is ohm minus 1 divided by log base 10 of modulus of ohm s by ohm p. So we have to substitute the values and we will get the n value as greater than or equal to 3.37. So rounding the n value to the next highest integer, that is 4. So if the normalized transfer function for n is equal to 4 is, that is if the 4 value means we have already seen that the denominator of h of s is be changed. So that is ha of s is equal to 1 divided by s squared plus 0.76537 s plus 1 into s squared plus 1.8477 s plus 1. To find the cutoff frequency, the ohm C is equal to ohm P by 10 the whole power 0.1 alpha P minus 1 the whole power 1 by 2 n. So that is ohm C is equal to 20 by 10 to the power of 0.1 minus 1 into the whole power 1 by 25. So we will get the answer. So the transfer function for ohms is 21.3868. So h of s is equal to ha of s for s is tends to s by 21.3868. So h of s is equal to this value for s is tends to s by 21.3868. For the next one, likewise we have to multiply and subdivision. The last answer will be finalized and we will get the answer. So determine the order and the poles of low pass Butterworth filter that has a 3 decibel attenuation at 500 Hz and an attenuation of 40 decibel at 100 Hz, 1000 Hz. So that is given. So next we are going to see about the given specification, that is alpha p is given. Everything pass band, stop band and the pass band frequency and stop band frequency, everything will be given. So we have to find out the answers. Likewise also the questions will be given. So next is the analog low pass Chebyshev filter. So there are two types of Chebyshev filter. One is a odd type 1 and another one is even type 2.